Alright guys, in this video we're going to be talking about how to calculate the pH of a salt solution. This is going to be slides 84 to 101. Alright, so buckle up. First of all, just to remind you, what is a salt? A salt is an ionic compound that is made by reacting an acid and a base. In this particular example, we have an acid where H is the hydrogen, proton, and X represents an anion, which could be something like chloride or perchlorate or nitrate, for example. Here we have our base. That base is represented by a metal hydroxide. So the M represents a metal, so metal hydroxide. When we react these two, this is a metathesis reaction where there's going to be an exchange of the ions. What we end up with is the cation from the base coming together with the anion from the acid in order to form our salt. This right here is our salt. And the other product of this neutralization reaction, it's water. You guys learned about neutralization reactions in General Chemistry 1, where we said an acid plus a base gives you a salt and water. So there you go. All right. So it turns out that when you place salts in solution, you place salt in water, if that salt is a soluble ionic compound, it will completely dissociate into the ions that it is made out of, where the metal ion, or the cation I should say, typically comes from your base, and the anion comes from the acid. And each of these two ions that are formed upon the dissolution of the salt has the potential to react with water in order to produce the acid or the base that it came from. So for example, this cation could react with water potentially in order to form the metal hydroxide base that it came from. Or this anion could react with water in order to form the weak acid or the strong acid that it came from. Such reaction with water is called hydrolysis. If an ion reacts with water through hydrolysis, then there's going to be a change in the pH of the solution. Depending on the salt and depending on the ions that that salt is made out of, the solution can either be basic, acidic, or neutral. And we're going to learn about how to differentiate whether a salt is going to generate an acidic, a basic, or a neutral solution. All right, so which ions actually do react with water? Only the ions that came from a weak acid or a weak base will undergo hydrolysis, meaning that they will affect the pH and generate either an acidic or a basic solution. So examples of ions that came from a weak acid or weak base would be acetate ion, which obviously comes from acetic acid, or the ammonium ion, which comes from ammonia, which is a weak base. These ions will have an effect on the pH of the solution, meaning that the solution will be either acidic or basic. Let's go ahead and write that down. Solution will be acidic or basic. Oops, not writing very well, am I? Let's see if I can erase. Oh, well, rats. Okay, acidic. And I did it again. Or basic. Well, you guys got it. All right, now the ions that do not react with water and thereby that will not affect the pH of the solution are going to be the ions that came from a strong acid or a strong base. The next page has a list of all of the ions that come from strong acids or strong bases. These ions are known as neutral ions, and the salts that are made from these ions are known as neutral salts. And those salts that have these neutral ions are not going to affect the pH, meaning that if you have a salt that has ions that came from a strong acid and a strong base, then you're going to have a neutral solution. Neutral solution would be one in which the pH is equal to 7 if we are talking about a temperature of 25 degrees Celsius. All right, here is the list of the counterions from strong acids and strong bases that will have no acid or base character, meaning that are not going to affect the pH of the solution. All of those are going to be the ions that come from the strong acids, so chloride, bromide, iodide, etc. And then here on the right hand side, we have the cations that come from strong bases. So this is going to be your group 1 metal ions and the heavy group 2 metal ions. Now notice that we have the sulfuric acid anion here as an asterisk because of the fact that sulfuric acid is a polyprotic acid. And so we're going to leave that one as a special case and leave it outside of this table. All right, so our job is going to be to predict whether a particular salt is acidic, basic, or neutral, depending on the ions that it came from. And so the first step that you're going to do is that you're going to take that salt and you're going to separate it or dissociate it into the ions that it is made out of. In this particular case, we're talking about sodium acetate. The ions that it is made out of are the sodium ion and the acetate ion. The second step is that we're going to be thinking about each of the ions independently, this guy and this guy separately, and we're going to think about whether those individual ions do or do not undergo hydrolysis. According to our previous pages, we said that only the ions that come from weak acids or from weak bases will actually undergo hydrolysis and react with water and thereby affect the pH. So if we start considering the sodium ion, since the sodium ion comes from a strong base, from sodium hydroxide, which let me just go and show you. There it is, sodium ion, right? Okay, so it does not affect the pH. Okay, so since the sodium ion comes from a strong base, it has no acid or base character. It will not react with water. It will not affect the pH of the solution. So we are done with sodium. Now we will consider the second ion, which in this case is going to be our acetate ion. Acetate ion comes from acetic acid. Thereby, it will affect the pH of the solution and it will undergo the hydrolysis reaction. That hydrolysis reaction is written by basically taking the ion, reacting it with water, and forming the weak acid that ion came from. If we had a cation instead, we would be forming the weak base that ion came from. In this particular case, that acetate ion is going to react with water by accepting a proton and forming the acetic acid that it came from. And what is left is what's left from the water after it has donated a proton to the acetate ion, which is basically the hydroxide. Now, the fact that we are liberating hydroxide ions into the solution means that we're going to have a basic solution. Okay, so again, the steps are going to be number 1, to dissociate the salt into the ions. Number 2 and 3 is going to be to look at each of the ions and think about whether or not they react with water through hydrolysis. And if they react with water through hydrolysis, meaning that they came from a weak acid or weak base, we're going to be looking at what the product is. That product, whether it's hydroxide or hydrogen ions, is going to dictate whether our solution is acidic or basic. If we liberate hydroxide, then the solution is basic. If we liberate hydrogen ions or hydronium ions, then the solution would be acidic. All right, next slide. This is basically the procedure. It's exactly what I just told you. Take a look at it on your own time, in case that it helps you to synthesize this idea in your head. All right. So another way to look at this is that the anions of strong acids and the cations of strong bases have no acid or base character. At the same time, the cations that are conjugate acids of weak acids will form acidic solutions. And finally, that the anions that are conjugate bases of weak acids are going to form basic solutions. So this is a good cheat sheet, if you would, that would basically help you to determine whether your solution is going to be acidic or basic. All right, so first example. We need to predict whether the following salt solutions are going to be acidic, basic, or neutral. And these are 3 independent problems. So we said that the first step was going to be to take that salt and dissociate it into the ions that it comes from. Those ions in this particular case are going to be the ammonium ion, NH4+, and the bromide ion. Next, we're going to be looking at each of the two ions and think whether each of those ions will or will not undergo hydrolysis. Remember that only the ions that come from weak acids or weak bases will undergo hydrolysis. So for example, we know that the ammonium ion is the conjugate acid of ammonia, which is a weak base. Therefore, this one will undergo hydrolysis. So I'm going to go ahead and take it, NH4+. I'm going to react it with water, H2O. And what I'm going to do is that this guy is going to be forming the base that it came from. It's going to be forming NH3. To become NH3, it is going to be donating a proton, and the water is going to be responsible for taking that proton. Therefore, what we're going to end up with is forming H3O+, or the hydronium ion, and that right there tells us that the solution is going to be acidic. And let's see if I can write acidic this time. Kind of. Oh my goodness, I don't know why I can't write with this pen. Anyways, we then look at the second ion. We have bromide ion. We know that bromide ion comes from hydrobromic acid, which is a strong acid, right? So Br- comes from HBr, and therefore it will not undergo hydrolysis. It will not affect the pH of the solution. Therefore, what we have, our answer is that the solution will be acidic, and we are done with that one. The second salt, NaCl. NaCl gets dissociated into sodium ions and chloride ions. We then think about each of the ions and what acid or what base they came from. Sodium ions particularly come from sodium hydroxide, and sodium hydroxide is a strong base. Therefore, the sodium ions will not undergo hydrolysis. Similarly, chloride ion comes from hydrochloric acid, which is a strong acid, and therefore that chloride ion is also not going to undergo hydrolysis. Because of that, neither of the two ions are going to affect the pH, and therefore that sodium chloride solution will be neutral. Awesome. Neutral meaning that the pH will be equal to 7 if we are at a temperature of 25 degrees. Finally, we have sodium cyanide. So we're going to take that sodium cyanide, we're going to separate it into the two ions, which are going to be the ammonium ion and the cyanide ion. We then think about whether each of those ions came from a weak acid or a weak base. And in this case, yes, we already know that the ammonium ion comes from ammonia, and so it will undergo hydrolysis, it will react with water, and it will be forming the base that it comes from, which is ammonia, NH3. In doing so, we know that it donates a proton and it donates it to water, so water is going to form H3O+. By looking at this, we would say that this particular ion makes the solution acidic, right? But then we also have to consider the cyanide ion. The cyanide ion comes from a weak acid, and so it will also undergo hydrolysis. It will also react with water, and it will be forming the acid that it comes from, which is hydrocyanic acid. What's left is the water after it has donated the proton to the HCN. Therefore, we're going to have hydroxide ions being released. And so this particular ion, the cyanide ion, will make the solution basic. And so now we have two contradictory things, and basically what this means is that depending on the equilibrium, depending on the K for each of these processes, the solution might, or one of the two processes might dominate, and so we would need further calculations. And that's as far as we're gonna leave it. Need further calculations, we basically don't know. So again, just to reiterate, if only one of the two ions is undergoing hydrolysis, then your solution will be acidic or basic depending on what it is that you are releasing. If you release hydronium ions, your solution is acidic. If you release hydroxide ions, then the solution is basic, like in the example in the previous page. On the other hand, if neither one of the ions undergoes hydrolysis, then the solution is going to be neutral. And finally, if both of the ions undergo hydrolysis, then further calculations would be required in order to figure out the acidity, or whether the solution is acid or basic. This table right here summarizes that information. It basically tells you that if you are starting with a strong acid, if you have a salt that comes from a strong acid and a strong base, then that gives you a neutral salt. If you have a salt that came from a strong acid and a weak base, then that's going to give you an acidic salt, where the hydrolysis equation between that cation is going to be generating hydronium ions, which tells you that the solution is acidic. On the other hand, if you had a salt that was made from a weak acid and a strong base, then the anion from that weak acid will be reacting with water through hydrolysis to form the acid that it came from and liberating hydroxide ions, which tells you that you have a basic salt. And if you have a salt that was made from a weak acid and a weak base, then it could go either way, and further calculations would be required. Now, the equations that I have written here, those are the equations, those are the hydrolysis equations that are the ones that determine whether the solution is acidic or basic. We will be using those hydrolysis equations in order to set up our ice charts to be able to calculate the pH of the salts. So make sure that you are able to write these equilibrium equations for the hydrolysis, which justify the pH in these reactions. All right, clicker question. When ammonium chloride is dissolved in water, the solution will be acidic, basic, neutral, or more information is needed. So go ahead and try it on your own. All right, let's say that you already tried it. So how do we solve this? Again, first step is to take your salt, ammonium chloride, and dissociate it in water. It is going to separate into ammonium ions and chloride ions. We then think about the two ions. Which of the two ions can we actually ignore? Which of the two ions are not going to react with water? And that would be this one. The chloride ion comes from HCl, which is a strong acid. Therefore, I don't need to consider it. On the other hand, the ammonium ion comes from a weak base, ammonia, and so I do have to look at the hydrolysis equation. Hydrolysis is where that ion comes and reacts with water in an equilibrium process, and it ends up forming NH3. And what is left is the water after it has accepted the proton in order to form the hydronium ion. And this right here tells us that the solution is going to be acidic. That's that. Next clicker question. Which of the following reactions is responsible for the resulting pH of a sodium acetate solution? I'll go ahead and tell you that all three choices, A, B, and C, are valid equations, but what I want you to think about is which of those equations actually tells us what the pH of the solution will be, meaning is the solution going to be acidic or is it going to be basic? So whenever we consider this, remember that the first step is to take that salt and dissociate it into ions. And if you notice, that's actually what A is. This is our salt being dissociated into the sodium ion and the acetate ion. However, that right there doesn't tell us whether the solution is acidic or basic. What does tell us that is the hydrolysis equation. So that's what we are looking for, the hydrolysis reaction. The hydrolysis reaction that is important in this case is not going to be the one with sodium, because sodium we know comes from a strong base, sodium hydroxide, and therefore it is not really going to be affecting the pH. Sorry. However, The acetate ion does undergo hydrolysis, which is what C is, and when it undergoes hydrolysis, it forms acetic acid, which is the weak acid that it comes from, and what's left is hydroxide ion. So this equation right here, which actually I should have written as an equilibrium equation, I apologize for that, that is the one that tells us that the solution is going to be basic, and so that was the answer to this question. That is that. All right. Next clicker question. Which of the following compounds will produce a basic solution when dissolved in water? All right, so your job here is to think about each of these salts. Hopefully in your head, we can start thinking about which ions we can ignore because they are neutral ions. They are ions that come from either strong acids or strong bases. And then from there, we can narrow down our options and finally just kind of concentrate on one or two of these substances that have a potential to react with water and give us either an acidic or a basic solution. And of course, we're going to be looking for the one that is a basic solution. So for example, we're going to start with A, sodium nitrite. The sodium ion comes from sodium hydroxide, which is a strong base, so that one does not affect the pH. The nitrate ion comes from nitric acid, HNO3, which means that is a strong acid, and nitric acid is a strong acid, and thereby the nitrate ion will not affect the pH. So this guy is a neutral salt. The solution of that salt will be neutral. So we are done with that one. Is there any other neutral salt in here? I wonder if you guys have seen it. So the other neutral salt in this list is sodium chloride. Sodium chloride has the sodium ion that comes from sodium hydroxide, which is a strong base, so it does not affect the pH. And then chloride comes from hydrochloric acid, or HCl, which is a strong acid. So therefore, this salt is also a neutral salt. All right, so we're left with the two in the center. Those two, they do have the potential to react with water, and so we're going to be looking at each of those salts. In this particular case, we know that the ammonium ion comes from ammonia, which is a weak base, so we do have to consider that. On the other hand, the chloride ion comes from hydrochloric acid, so we can actually kind of ignore the chloride ion because we know that that one will not affect the pH. So I'm just going to take my ammonium ion, and once more I'm going to go and react it with water. I know that the ammonium ion is going to be acting as an acid, donating a proton in order to be able to form the base that it came from, which is ammonia. And in doing so, it donates the proton to water, forming H3O+ or hydronium ion, which tells us that the solution is acidic. So that is also not our answer because we're looking for a basic solution. So last we look at the sodium carbonate. Of course, we can ignore the sodium ion because sodium comes from sodium hydroxide, which is a strong base, so it will not affect the pH. However, the carbonate ion we do have to worry about, and so I'm going to take my carbonate ions, CO3 2- charge. I'm going to react them with water, and what happens here is that that carbonate ion is going to accept a proton. That's the only thing that it can do, right? It cannot donate a proton because it has no protons. So it will be accepting a proton, forming HCO3 with a -1 charge. And what is left is the water after it has donated that proton to the carbonate, meaning that we're going to be left with OH- or hydroxide, and that tells us that our solution is in fact basic, which is the reason why this particular salt is the only one in the list that gives us a basic solution. I hope that made sense, guys. Oops, sorry. No. Sorry. Had a little oopsie there. All right, let's go to the next slide. Next clicker question. Which of the following substances will give an aqueous solution of pH closest to 7? Go ahead and pause the video and give it a try. Please, 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 pretty please, do it yourselves. All right, so hopefully you guys were able to get this one. We're looking for a pH closest to 7, which means that we're looking for the only neutral salt that is going to be on the list, right? That means a neutral salt. And first of all, in the list here, I had a combination of salts together with some molecular compounds and some bases. Hopefully you were able to see that. Let's go ahead and start ruling out. Let's see. Let's look at this guy right here, D. This is ammonia. Is that a salt? No. Is that an acid? No. We know that ammonia is a base. Is a base going to give you a pH that's equal to 7? Well, no. So we can go ahead and rule that one out. Now, is there any other substance in this list that is a weak base similar to ammonia, or basically an amine base, a base that is derived from ammonia? Well, in fact, there is. Let's look at E. Notice that E has a nitrogen as a central atom. It has 2 hydrogens, 1 and 2 right here. And then we have one of those methyl groups that we talked about in a previous video. What that means is that this is a base that is identical in structure to ammonia, but where we have replaced one of the hydrogens with a methyl group. And so this guy is also a weak base. It's a weak base going to give you a solution that is neutral? Well, no, it's going to give us a basic solution with a pH greater than 7, just like ammonia. So we can go ahead and rule this one out. All right, from there, is there anything else that is not a salt in this particular case? And the answer is yes. Look at CO2, that's carbon dioxide. Carbon dioxide is a molecular compound. And you guys might or might not know this, but when you put CO2 into water, it actually forms carbonic acid. And in fact, I actually had that equation for you guys in the exam that you just took the week before spring break. We had the dissolution of CO2 forming carbonic acid. So anyways, this one is going to form carbonic acid in water. Therefore, it is not going to give you a solution that has a pH of 7. It will give you an acidic solution. So this one can be ruled out. And that one was a tricky one. Now, what we're left with is 2 different salts. Out of those 2 salts, I'm hoping that you're able to identify that this one is the one that is a neutral salt. And the reason for that is that the potassium ion comes from potassium hydroxide, which is a strong base. And I'm going to go ahead and write this. So this has potassium ions and it has nitrate ions. Potassium ion comes from potassium hydroxide, which is a strong base, and therefore potassium ion will not undergo hydrolysis, will not affect the pH. Nitrate ion comes from nitric acid, HNO3, which is a strong acid, and therefore that nitrate ion will not undergo hydrolysis and it will not affect the pH. So that meant that we had a neutral salt. The last one, ammonium iodide, that one actually will affect the pH. It will be, in this case, acidic. And the reason for that is that it is made from ammonium ions and iodide ions. The iodide ions we actually can neglect because of the fact that it comes from hydroiodic acid, which is a strong acid, and therefore it will not affect the pH. But the ammonium ion will affect the pH. We've already done it a couple of times, and we know that when this guy undergoes hydrolysis, it will end up liberating H3O pluses, which means that the solution is acidic. So our answer was A. Sorry, guys. This is the type of question that you will see in an exam. So I do want you guys to be able to, take your time, analyze each of the compounds and be able to figure out which ones are acidic, which ones are basic, which ones are salts, which ones are weak bases, which ones are weak acids, etc. Okay? All right. Now, here we're going to be talking about how to actually do the calculations to figure out the pH of a solution. The process is that, first of all, we're going to dissociate the salt into the ions, just like we have already done. Then we're going to determine which of the ions undergoes hydrolysis, and we're going to write the equilibrium reaction for this hydrolysis, meaning that we're going to put the ion plus water, and then we're going to figure out what the products are, and we're going to use that equation to set up our ice chart. We then are going to use Ka or Kb depending on what behavior the ion is undertaking. If the ion is accepting protons, it means that it is acting as a base, in which case I will need a Kb. While if the ion is donating a proton, that means that it is behaving as an acid, and in that case I would use the Ka. Once we use our ice chart and our Kb, we will solve for X, and that X will represent either the hydrogen ions or the hydroxide ions, and from there we can calculate the pH or the pOH and answer whatever question we were being asked. All right, let's go ahead and try it out. So, the question is, calculate the hydroxide ion concentration and the pH for a 0.1 molar sodium cyanide solution. The Ka for hydrocyanic acid is 4.9 times 10 to the 10. All right, let's get ready. So we have a solution of a salt, sodium cyanide. First step is that we're going to take that salt and we're going to separate it or dissociate it into the ions that it is made out of. Those ions are going to be the sodium ion and the cyanide ion. And if you don't mind, I'm going to go ahead and write the concentration of it right under here, just to remind me. I had a 0.10 molar solution of sodium cyanide. When this one dissociates, it completely separates, meaning that we're going to have a 0.10 molar sodium ion concentration and also a 0.10 molar cyanide concentration. That's just for me to keep in mind right now. All right, the second step was that we were going to think about each of the ions. Which of those two ions can we ignore? Well, the sodium ion comes from sodium hydroxide, and we know that sodium hydroxide is a strong base. Therefore, that sodium ion does not affect the pH, and we can go ahead and ignore it. On the other hand, the cyanide ion, we know it comes from hydrocyanic acid, and we know that hydrocyanic acid, it's a weak acid, and therefore that cyanide ion will affect the pH. So we're going to take that cyanide ion, Cn-, and we're going to react it with water in the hydrolysis equation, and we're going to see what we're going to form. Remember that this is an equilibrium process, right? What is it going to form? Where we just said that Cn- comes from HCN, the hydrocyanic acid. So that's what's going to form. And in doing so, that cyanide accepted a proton from water. Water donated the proton, which means that now water has become a hydroxide ion. Just by writing this equation, we already know that our solution is going to be basic. And so this is something that is good for us to keep in mind as a way to double check our answer in the end. This equation is the equation that we're going to use to set up our ice chart, initial, change, and equilibrium. What is the initial concentration of cyanide ions that I have? Well, according to our first step, we said that we had a solution that was 0.1 molar in cyanide ions. Initially, for water, actually, we don't care because that water is a pure liquid, and so it will not be participating in our equilibrium. Now, the products. Initially, I don't have any of those products because that cyanide ion is just about to start reacting with water. So initially, I have 0 for these two. We then go to the changes. The change for the cyanide ion is going to be -X as it is used up. And for the products, it's going to be +X and +X. From here, we continue. We basically add up our column. The equilibrium concentration is going to be 0.10 - X for cyanide ion. And then 0 + X is X, 0 + X is X for our products. We then have to think about whether we need to set up a Ka or a Kb equation. And that is not going to be dependent on what is given to you. Notice that we were given a Ka. That doesn't matter. What you need to do is to come back and look at your cyanide ion right here. What is that cyanide ion doing? Well, as we go from here to the right-hand side, it accepted a proton. And if it accepted a proton, that means that that cyanide ion is acting like a base, right? It accepted a proton, so it is acting as a base. That means that I need to use a Kb. All right, so I'm gonna set up my Kb equation. That Kb equation is gonna be equal to our products divided by our reactant concentrations. HCN times the hydroxide ion concentration divided by the concentration of the cyanide ion. And of course, remember that the water gets omitted because it is a pure liquid. Now, do I actually have the value of Kb? I do not. I have the value for Ka. And so somewhere on the side, we're gonna go and say, okay, I know that I can find my Kb by taking Kw and dividing it by the Ka. So our Kb is gonna be equal to 1.0 times 10 to the minus 14 divided by the Ka, which is 4.9 times 10 to the minus 10. The Kb is therefore equal to 2.0 times 10 to the minus 5. Awesome. So now I have my Kb. I'm going to go ahead and replace the concentrations with our equilibrium line in the Kb equation here. So for the hydrocyanic acid, we have X. For the hydroxide ion at equilibrium, we have X. For the cyanide ion at equilibrium, we have 0.1 minus X. Okay, let's go ahead and make more room here. I'm going to rephrase this as Kb equal to X squared divided by 0.10 minus X. And now I know that that Kb is 2.0 times 10 to the minus 5. Now, to be able to solve for X, I can either use the quadratic equation, which I really do not recommend, or we can go and make an assumption. Since the Kb is so small, we can assume that this X is very small. So assume that 0.10 minus X is more or less equal to 0.1. And that means that our equation can be simplified to be X squared divided by 0.1 is equal to 2.0 times 10 to the negative 5. From there, we get that X squared, actually, I went ahead and solved for X, sorry. But basically, you take the 0.1 to the other side, that gives you X squared. Then you take the square root of both sides and you end up with X is equal to 1.4 times 10 to the minus 3. And then we come back to the ice chart and we say, okay, what is X that would help us? Well, according to the ice chart, notice that X represents the hydroxide ion concentration at equilibrium. And so that's what I'm going to come back here and label it as. This guy right here is our hydroxide ion concentration at equilibrium. And if we go back to the very top, notice that the first question was to calculate the hydroxide ion concentration at equilibrium. So we have done that. We have answered the first question. That is the first answer. The second question was to find the pH of the solution. And we know that we can find the pH of the solution by taking the hydroxide ion concentration, converting it to a pOH, and then from there finding the pH. Or alternatively, you could take the hydroxide ion concentration and using the Kw equation, you could have found the hydrogen ion concentration, after which you could take the negative log of that and find your pH. I'm going to go with this first method. So what I'm going to do is that I'm going to find the pOH by taking the negative log of my hydroxide ion concentration, which is the negative log of 1.4 times 10 to the negative 3, and that gives us a pOH that is equal to 2.85. From there, we then are going to use the equation that says that the pH is equal to 14 minus the pOH, or in this case, 14 minus 2.85, meaning that we have our answer as 11.15. And now we are done. That is our second answer. That is the pH of our solution. The last thing that I want you guys to do is to check your answer, right? One of the things is that at the beginning, we said that the solution was going to be basic right here. And so we go back and double check, is this a basic solution that has a pH of 11.15? Yeah, we expect the pH to be greater than 7 for sure. The other thing that I want you guys to check is whether your assumption was correct. So one of the ways to do that is to take the 1.4 times 10 to the minus 3 divided by the starting concentration, which was 0.1, and see if it is less than 5% of that starting amount. And yes, in this case is a 1.4%, so our assumption was valid. And now we are done. All right, guys, now we move on to a clicker question. So, and actually before I move on, just in case that this helps, let me make this a little bit smaller so that you can see the whole problem in case that you want to just kind of take a snapshot and take a look at the whole process in one screen. All right, that should do it. Let's move on to the clicker question that follows. When KCl is dissolved in water, the solution will be what? Acidic, basic, or neutral? Hopefully you're going to get this one in 2 seconds. You know that KCl has potassium ions and chloride ions. Potassium comes from potassium hydroxide, which is a strong base. Chloride comes from hydrochloric acid, which is a strong acid, which means that your solution is going to be neutral. And the next clicker question, when sodium carbonate is dissolved in water, the solution will be what? Well, hopefully you can do this quickly as well. You can see that sodium comes from sodium hydroxide, and so we don't have to worry about it. The only ion that we have to worry about is the carbonate ion. And so what you do is that you take that carbonate ion, you react it with water. The carbonate ion is going to act as a base, accepting a proton, since it cannot donate a proton because it has no protons. So it would form a hydrogen carbonate. And what is left after that process occurs is what's left of the water after it donated the proton, which means that we have hydroxide being formed, which means that we have a basic solution. And with that, we have finished this section. All right, guys, I will see you on the next video. Have a great time. Bye.